In this video I'm going to explain how RAM memory works. I've added a RAM circuit to the model CPU. There's two types of RAM memory, dynamic RAM and static RAM. Dynamic RAM uses capacitors and transistors to store bits of data. This is cheaper, but it's slower than static RAM. Static RAM is what I've built for our model CPU, and this uses flip-flops to store bits of data. So let's have a look at this circuit and let's break it down one stage at a time and see how I've built it. Okay, so I've built a memory circuit with 16 cells. Up here at the top left we've got 4 switches, and this is how we're going to address our cells of memory. Each of the switches is connected into 2 lines. One of these lines is connected directly and the other one is going through a NOT gate. And then around the circuit we have some AND gates. The AND gates on the left are controlling which row we want to address, and the AND gates at the bottom are controlling which column we want to address. So we have 4 AND gates on the left. The first one is connected to the NOT line of both of the least significant bits. The next one is connected to the NOT line of the second digit, but it's connected directly to the least significant bit. And then the next one down is connected to the NOT line of the least significant bit, but directly to the next bit. And the bottom row is connected to both bits directly. So if we see, we're currently selecting this top row because this line here is active. If we switch on the least significant bit, this goes off because this line is now off, but then the next AND gate activates and we activate this row. If we switch on the second least significant bit, we activate the next row, and if we switch on both of the least significant bits, we activate the bottom row. Exactly the same thing is happening at the bottom here, but this is addressing the columns. So now we have the left hand column is active. If we switch on the second most significant bit, it activates that line. The most significant bit activates the next line, and both of the most significant bits activate the next line. And then what those lines are doing is both the rows and the columns are connected into AND gates, and they're activating the LED in the cell to show that we're addressing that memory. So if we see we're currently addressing the top left cell, if we want to move across we can switch, or move down we can switch on these 2 bits. If we want to move across we can switch on these bits. So we can see that each time we switch a switch we'll be addressing a different memory cell. We have 16 possible input values and 16 possible cells, and when we switch the switches we're switching which memory cell we want to address. Now in this example I've just extended it slightly by adding an address register. So whereas before we just had 4 switches, now I've added a little register with flip-flops. So our 4 switches, we can select which address we want to access, let's say 1001. But the memory address in the cells doesn't flip until we activate the address register and send a clock pulse. And that flips to the address we want. So CPUs usually address their memory with an address register. We need to hold the value of the address that we want to read or write, and then we can do our operation in memory when the value is in the address register. Okay, so now I've put a circuit like our register into every cell. That's 8 flip-flops which will hold 8 bytes of data. The flip-flops will load data when the clock signal comes in and also when the input line is switched on, and they'll output data when the output line is switched on. That's just like a register that we built before. the circuit that we made to say which cell we're addressing is being ANDed with the input and output lines before it goes through to the series of flip-flops. So the input switch is connected to every cell in memory, and so is the output switch, but because of these additional AND gates, so the input gate is being ANDed here with the cell address output, and the output gate is being ANDed here with the cell address output. So the input and output switches for the memory will only work on the cell that we're actually addressing. So we're currently addressing this cell upper left here. If we want to load the value 1 into it, we can switch on 1 into the input data, and we can see that 1 is flowing into every cell of the memory. When we switch on the memory input switch and send a clock pulse, we should see that just this cell that we're addressing flips to the value 1. So there we have 1. We switch off the memory input and switch off the value on the bus. You can see that we've held 1 in that value. Now if we address this next cell, which is 0100, switch on the memory address input, a memory address register input, and send a clock pulse to flip so that we're now addressing this cell. Now let's put the value 2 into that cell, so we will switch on the value 2 onto the input bus, switch on the memory input and send a clock pulse, and there we've loaded 2 into this cell, and we've still got 1 in this cell. Now if we switch off the input bus, I'll now put 0 back into the address register to readdress this cell. And if we now switch on the output doesn't require a clock pulse. It will just output whichever cell we have addressed. So that's the 1 value that we put into this upper left cell. Now if we readdress this cell, let's see if we can put this 2 back onto the bus. So 0100 in the address register. Send a clock pulse to load that. And if we switch on the output now, we see we put the value 2 that we put into this cell. So with this circuit we can select the address we want to use, and then we can input values from a bus according to the clock pulse. We can put those values in those cells, and then we can also address the memory and output the values back onto the bus. So now let's take this and add it to our model of a CPU. Okay, so I've taken a 16-byte memory circuit and added it to our model of a CPU. So over here we have our CPU model that we've built in previous videos with 2 registers and an ALU. And it has a common bus, which are these vertical lines running through here. We've connected the address register that we've moved over here onto the right of the memory circuit to the 4 least significant bits on the bus. And we've connected the bus input to the memory and also the output to the memory back into the common bus. So what I'm going to do is I'm going to put a value in register A, move it into memory, and then move it back into register B, just to demonstrate how we can move values from the registers into memory and back out again. So first I'll put the value into register A. So let's say the value 5, so 4 plus 1. So if we switch on those values on the bus, 4 and 1, switch on the input to register A and send a clock pulse to load the value 5 into register A. We'll switch off the input and the input to register A. We want to move that into memory. If we put it into this cell, say, because it's easiest to see because it's closest to us, the address of this cell is 1100. So we need to load that into the address register. So we're only using the 4 least significant bits. So 1100, address register in, send a clock pulse, and we can see that this LED has come on to tell us that we're now addressing this cell. Now we want to take the value 5 and move it into there. So we switch off the bus input and the address register input. We'll switch on the output from register A. We can see the value 5 now is on the bus and it's flowing into all the memory cells. Switch on the memory input and the memory cell still doesn't contain the value, but we send a clock pulse and now we've taken the value 5 and moved it into the memory cell. Now we want to take that value out of there and put it in register B. So switch off the memory input, switch on the memory output, switch off the register output and switch on register B input and send a clock pulse. And there the value has come out of memory and gone into register B. So now we can transfer values around in and out of memory to the registers. So we've got 16 bytes of RAM in our model CPU. So now instead of simulating all of the memory cells, I'm going to add a chip to the model. We did have 16 bytes of RAM modeled before, but it was getting quite heavy for the simulator to simulate. And it was getting quite busy in the diagram, so I've added a chip. This is a 256 byte RAM chip. So as we did in our RAM circuit, we have the clock input and we have the input and output lines, and now we've got 8 address lines because it's a 256 byte chip. So we have the address lines coming in and then we have 8 input lines and 8 output lines. So it works exactly the same as it did in our 16 byte circuit. So if we want to load the value 0 into the address register, we switch address register input on, 5 o'clock pulse. Now if we want to load the value 1 into address 0, switch value 1 on, memory in, send a clock pulse. So we have 1 in address 0. Now if we go to address 1, we keep 1 on the input. Address 1. Now we're addressing 1 in the RAM. And we'll load the value 2 into address 1. So memory in, clock pulse. So now if we go back to address 0 by loading 0 into the address register and switch on the output, we can see we've got the value 1 in address register 0. If we load 1 into the address register, and then we output that, there's the value 2. So we've loaded the value 1 into address 0 and 2 into address 1. So everything's connected to our common bus still, but this time we've got 8 address lines. We've got a 256 byte RAM chip. So now with our CPU model, we can load values into the registers. We can perform calculations on the numbers with the ALU and test to see if certain conditions are met with a flags register. And now we've got 256 bytes of RAM that we can load values into and pull values out of. What we're having to do is flick on and off all these different switches that we've got. What we really need is a computer to be able to run a program. So in future videos we're going to look at the control logic and how we can get the computer to do these things itself, how we can program it to do things. So if you've enjoyed this video, give it a like, and if you'd like to follow the CPU model as we create a full CPU, then please subscribe. Thanks for watching.